if you have a matrix, you can call norm function in different ways to find the different definition of the norm. And this example is not well chosen because the sum of each, this is a matrix matrix. So the sum of each row and each column and the diagonal elements are the same. So we cannot find the difference between norm 1 and norm infinity. So if you try different matrix, you may find that the values of the norm might be different. But normally they will represent the same scale. I will explain to the application of norms later on. So now let's consider the characteristic polynomials of a matrix. By definition, the characteristic polynomial is something like this. If you use an operator S, the times identity matrix and minus A, we have a new matrix containing N. And if we find that the determinant of this matrix, what we find is a polynomial of S. And this polynomial is called the characteristic polynomial of the matrix. And also the roots of the polynomials will be exactly the same as the eigenvalues I will discuss later of the matrix. So we can find the characteristic polynomial in this way. And normally, if we want to extract a polynomial in Matlab, what we need to do is to compose a row vector containing all the coefficients in descending order of S. So we can use this one to describe the polynomial. The polynomial of a matrix. And the question is, how can we find the characteristic polynomial of a matrix? So what we need to do is call the poly function in Matlab. And then we can find the polynomial of the matrix. And C here will be the vector containing all the coefficients of the matrix. And if A is a symbolic matrix, what we obtain here after call of the poly function, the C will be the mathematical representation of a real polynomial. I will explain this by example. Let's go back to this matrix again. If we want to find the polynomial of it, characteristic polynomial of it, what we need to do is first enter the matrix and then call the poly function. And this is the result of this polynomial. And call that again. This is the result of the polynomial. And you have multiplied 1,000 to each element there. So the coefficient here is 1 minus 34, 8 minus 80, 2,720, and 0. So the coefficient of this is something like this. And you may see that there might exist errors in this result. So what we need to do is to let C1 minus 1 minus 34 minus 80 2,720 0. And we find that there are differences. This means that the poly function may result in, if you call the poly function, you may find the result with errors, although the error for this example is very small. And if you are using a symbolic math toolbox, first you need to do is to convert it into a symbolic matrix A and then call the poly function. And you will find the accurate result. So we see this is accurate results. All the coefficients are integers rather than the results we have already obtained there. So there is a problem with the numerical polyfunction. If you use the numerical function, the algorithm it used is not good enough. So normally we will introduce another better recursive algorithm like this. It is called the Lagrangian algorithm. And this is another algorithm not implemented in Matlab. And it is a recursive algorithm. To use the algorithm, first we have to define that R1 is the identity matrix and C1, which is the coefficient of the polynomial, is 1. And then if we go back to this formula, we will see that we can find C2 and R2. If we have C2 and R2, and if we go back to this formula again, we can find C3 and R3 until we can find all the coefficients, polynomial coefficients of the matrix. And it should be noted that in this computation, we can see that there are only multiplication of matrices and sum of matrices. So the error using this matrix, using this algorithm might be very small. And in the polyfunction provided in Matlab, they use the eigenvalue-based algorithm. And eigenvalue-based algorithm is an iterative method, based on an iterative method. So there might be errors. But with the use of this algorithm, we need only perform multiplication of sums of matrices. So there shouldn't be any error. So based on this algorithm, we can write a program to implement it. And we can use the loop function of this kind of algorithm. I'm not going into too much detail about it. And this is the kernel part, this is the central part of the poly1 function I wrote myself, based on the Lagrangian algorithm. And the syntax of the function is also poly1, which is similar to poly function.
And what is the disadvantage of this? Why Matlab doesn't?
There shouldn't be any error.
But why Matlab doesn't implement this one?
I don't know. They use the eigenvalue-based algorithm, so that might be a problem. They use the iteration in EIG, and there should be an error tolerance. So if you use this one, there shouldn't be any error. Only one. Okay, so you can get the result, the accurate result directly. And also the one provided by Matlab may give misleading result. I've shown this by example later on. So with the use of poly1 function, then you can get an accurate result. This is the code for poly1 function. It